Hey everyone, welcome into lecture number 24 of the semester. This lecture is on probability, and let's just get into it and define what we mean by a probability density function. So this is going to be the main topic of study in this section, a probability density, whoops, spelled wrong, density function. All right, that's way too many letters for me to constantly write, so I'm going to call this thing a PDF. In the future, probability density function. This is a it's a function, of course, right? So it's a function f satisfying these two criteria. All right, so number one, I'll just put these as bullet points, but f of x is defined and greater than or equal to 0 for all x in the real number line. Okay, so it's defined and greater than or equal to 0 for all real numbers. And then number two, this is what makes it a probability density function. I mean, this is part of it, it's criteria. But the second criteria is the following, that the integral from minus infinity to infinity, so the integral over its entire domain of f of x dx has to be equal to 1. All right, and so that 1, that's the probability that anything happens here in your domain, any x values occur. So let's see how this works. So suppose, by the way, we usually, I'm not going to get into all of the statistics of it, but in statistics we talk about random variables. So capital X here, this is going to be thought of as a continuous random variable. And so this is like an event that could happen. I'm not a statistician, so don't, maybe I'm going to say this slightly differently than a statistician would. But a continuous random variable is an event that could happen, and it's described by this probability density function. So the probability that, say, x is between, and x has got some numerical value here, right? So x is between a and b. This is the probability that exactly what happens in here is true, right? So that capital X, this continuous random variable, falls between these values of a and b, and this is given by the integral from a to b, actually, not the entire integral over the entire interval, but the integral from a to b of f of x dx. And because of these two criteria, what does this mean? Well, this means that this number can be anywhere between 0 and 1, but it's at most 1, and it's the least it can be is 0. 0 would mean that there's no probability that this happens, right? 1 means that there's 100% probability. It will happen. There's 100% certainty. And any number in between there measures the probability, right, that this event will happen. All right, so we're going to take this from a mathematical point of view, but you'll see this again in your future courses, I think, if you take stats for sure. But let's do a couple of examples, and then we'll leave this section here. But here's an example. Let's say I give you a function f of t is equal to, it's piecewise defined, so it's equal to 0 when t is negative, and it's equal to some number capital A times e to the minus ct. So for two constants here, a and c, for t greater than or equal to 0. So the criteria here is that c must be a positive constant. It's got the minus sign here, so we want the shape of the curve. I'm going to sketch the graph in a second. And then a has to be a constant that, which in concert with c makes our integral obey this property, right? So we're going to have to compute a. And in general, what this looks like, this graph, it's going to be positive, so we don't have to worry about having any negative region here. I guess that should be a t the way I define this. Here's our t, here's our probability, our f, you could say. And this graph is going to look like the following. It's constant 0 on this side. By the way, that means there's no probability of any of these items happening, right? And then whatever a is, it jumps up to a here, but the probability of that one event is still 0, because you integrate from 0 to 0, you still get 0. And slowly this is going to taper off, right? And then the criteria has to be that this integral is not only convergent, not only finite, but that area is equal to 1. Okay, so that area has got to be equal to 1. And again, our function, our probability density function, after we compute this a, is going to be given by this formula. So this a needs to be computed to guarantee that this integral is 1. So let's do it. What do we have to do? Well, we just have to compute that integral, right? So the integral integral from minus infinity to infinity of our function. So it's a e to the minus ct dt. First of all, we know that our function, that's not true. This is not what we want to compute. I have jumped the gun. We want to compute the integral of f entirely, right? So I messed up. So we want to compute the integral of f, and then we notice that our function is 0, right, for all t less than 0. So now I can make that change, but what do? I have to break up the integral from minus infinity to 0. I'll write out all the steps here. Plus the integral from 0 to infinity. You can always do this, right? On this portion, the equation of the function is this. It's 0, right? So this integral is gone. And on the other portion, the equation is this. So now we have to integrate this. But notice that's not what I wrote the first time because the lower bound is 0, right? So what we have to compute is this should be the integral from 0 to infinity of a e to the minus ct dt. A is a constant, so it can come out. And then we have to treat this with a limit, right? We have to use a limit. So we're going to use the limit. Let's use a u. As u goes to infinity, the integral from 0 to u. That's how we define an improper integral, right? E to the minus ct dt. Now we compute the antiderivative. So this becomes a times the limit is still here. U approaches infinity. What do we have here, though? Antiderivative of e to the minus ct is minus 1 over c. E to the minus ct, and then we're going to plug in our t equal to 0 and u, of course, right? And we then obtain a times the limit as u approaches infinity of negative 1 over c e to the minus cu, we're going to have to think about that, plus 1 over c e to the 0. All right, now because of our condition that c was a positive number, right? We don't care what positive number c is, but c has to be positive. Because of this condition, then this limit, right? This limit's going to act here on this term, and as u gets very large, e to the minus very large becomes very small, right? So this limit is going to approach 0, and that's the only place the u shows up anyway, right? So after all this work, and e to the 0 is, of course, equal to 1, right? So after all this work, what do we end up with? We end up with a times 1 over c, right? A times 1 over c. And now we have to remember what our goal was. Our goal was to make this integral equal to 1, right? Our goal was to find a that forced this integral to be equal to 1. Well, what's a have to be now? You can multiply over, or you can just do this by inspection. But this tells us then that our a has to actually equal c, and we can go back up and answer our question, which I guess I didn't write down specifically, but the question is, what does a have to be to make this a probability density function? And so the answer is our probability density function is now given by f of t equal to 0 when t is negative, and c e to the minus ct when t is greater than or equal to 0. And remember, c can be any positive number here. Okay, c can be any positive number. All right, so there's an example of a probability density function. Let's define a couple more statistical objects here, and then we'll come back to this function. Actually, we'll compute them. So we're going to define some averages. So we are on item 3 now, I believe. So mean and median. I'm going to sketch a picture of each of these, okay? So the idea, there's two ideas here. We've got our probability density function has a graph, right? So I'm going to draw a probability density function that you might have seen, and we'll talk about this one at the end, actually. But maybe you've got a graph. Maybe this won't be exactly what we've seen. Maybe we've got a graph of a function that looks like this. Okay, so there's our t-axis again, and our f-axis up here. And of course, we can, if this is going to be a probability density function, we can just assume that this area is equal to 1. All right. Now, this region has a center of mass. Right? So the center of mass, let's just guess. I'm going to maybe draw it so it doesn't look exactly right. But maybe the center of mass for this region is right about here. Okay, so in our mind, let's just suppose that this is a center of mass. Now, it's weird to call this the center of mass because what's the mass, right? This is a probability density function. It's not really a mass, right? There's no mass here. But we can do the same computation that we did in in the previous section, in section 8.3 of our text, when we actually studied centers of mass. And, you know, this is another name for this is the centroid. But this x value, the x value where the center of mass occurs, this is called the mean of the distribution of the PDF, right? The probability density function. And this mean is the average, right? It's like the average of the probability density function. So mu is equal to the mean, and its formula, it's really the x bar of our center of mass, right? So I'm sure you remember that to compute the center of mass, the formula is you integrate over the entire domain, which is in negative infinity to infinity. You integrate the function, so to find the x component, right, of the center of mass, you integrate the function x times f of x dx, but then you have to divide through by the entire mass. So this is the integral from negative infinity to infinity of just f of x dx. But with our probability density function, what do we know about this integral right here? This integral has to be 1, right? So actually the mean is simply this integral that's in the numerator here. So negative infinity to infinity, x times f of x dx, this is equal to mu. So that's the mean. And again, the mean is just the x component of the center of mass. The y component is not, at least as far as I know, it's not statistically relevant because this distribution could have, you know, many different shapes. But the x component is definitely relevant. It corresponds to the mean or the average that we're used to from statistics. There's another kind of average. So when I say mean, I should say mean. I shouldn't say average, right? Because there are different ways to measure averages. Another way is to just find the median. Well, what does the median mean? The median is like the halfway point in the distribution, right? So the median is going to be different. The median, this is the center of mass that includes the height somehow, right? The median is going to be the x value for which, when you cut this thing in two parts, that it cuts the area exactly in half. All right, so it cuts the area exactly in half. So this we're going to call lowercase m. They might be close together. They might be the same. They might be really far apart. Okay, the mean and the median. They might not be that close together at all. It totally depends on the distribution. So the median is defined to be. There's two different ways we can do it. What's it got to be? Just looking at this, you can think about criteria for the median. It's got to be the x value for which, when you integrate up from negative infinity to m, you get half of the total area. Well, half of the total area is a half because the total area is 1, right? Or you could go in the other direction. You could start at m and go to infinity. So it happens, so there's two different ways to write it. It's not equal to this formula, right? But it's the m that satisfies this formula. It's the integral from minus infinity to lowercase m of f of x dx. It's got to equal 1/2, right? So it's defined implicitly by this formula. Or, on the other hand, it could be the integral from lowercase m to positive infinity, because obviously if you cut this thing in half, then both halves have the same, you know, area, which is equal to 1/2, right? So this is the mean and the median. The mean and the median. Let's do an example. Let's find the mean of our distribution from up above. So we'll leave the median for some homework assignments, but let's find the mean of this distribution. Find the mean of, you can easily find the median as well, so I'm going to leave that as an exercise, but find the mean of this one. Remember, our function was 0 when t is less than 0. And it's c, we found that number, right? C e to the minus c when t is greater than or equal to 0. We don't care what c is, but it's going to be positive. Okay, so let's compute. This is, again, we're going to try to find the mean. So let's sketch the graph just so we can see what's going on, and then we'll compute it. We just have to compute a formula, right? So here's our f and our t. Our graph, again, looks like this. And now we know it goes up to c here, and then tapers off this way. And we want to try to find the center of mass of this whole thing. So obviously the center of mass is not going to be over here, right? It's going to be over here somewhere. And this x value here is going to be our mu, right? So the x value where that center of mass occurs. All right, let's compute it. Really, we don't have to draw this to compute it, but it's helpful, I think, to see it when you're first learning this so that you can think it through. So let's compute. Our mu is going to be equal to the integral from minus infinity to infinity of t times f of t dt. I keep switching between x's and t's, partially because it's just an integration variable, and you have to get used to it. So, but it doesn't matter, right? It doesn't matter what this variable is. We're going to do the same thing we did before, right? We already know that this function is 0 on this portion, and then we're just going to integrate it up on this portion, right? So actually what we have to compute is the integral from 0 to infinity of t times c times e to the minus ct dt. All right? And you can probably guess this one has to be done by integration by parts, right? It has to be done as integration by parts. So what are we going to do? We're going to let this be our u, and that leaves all of this to be our dv, and let's compute it. So we've got u. We can do this by our table method, right? So this is really ct, c0. We've got our dv. It's going to be e to the minus ct. That's all we're taking for the dv, right? Times dt, of course. And then minus 1 over c, e to the minus ct. And then 1 over c squared, e to the minus ct. And we know how to do this. So the integral is going to be this times this minus this times this, right? So let's compute. So, by the way, we have a limit in here that I have not dealt with properly, so I'm going to be very careful now to write this out. So I'll write it in 2 steps and then we'll write this back out. But we need to deal with this improper integral, right? So the limit here, I've already used u. Let's do this as s now. We could do capital A in this case. I think the book uses capital A, but let's use s to infinity. This is then the integral from 0 to s, and we're integrating the same thing. I'm just rewriting this because I should have done this first, right? And now we know that this becomes the limit as s approaches infinity of our antiderivative, that part we've got now, right? So that's going to be negative t, negative ct over c. So that's just negative t e to the minus ct, right? Minus, and this one is just going to leave us with 1 over c e to the minus ct, and then plus 0. And we're going to plug in our t values of 0 and s, and then compute the limit, right? So let's see. When we plug in s, what do we get? We had now the limit really matters here. We have the limit as s approaches infinity of minus s e to the minus c times s minus this becomes 1 over c e to the minus c times s. This one we know what to do with. We're going to have to talk about this one. And then we're going to subtract from this, so it's going to change these to pluses, right? We're going to plug in 0. So plus 0, when t is 0, this one's 0. Plus, again, we're subtracting, right? So plus 1 over c e to the 0. So that's 1 over c. All right? We know what happens to some of this. So this portion as c, 1 over c is a constant, right? As s goes to infinity, c is positive, so this approaches 0. So that one's going to be gone. What about this one? Well, this one I'm going to leave for you guys to actually do it, but you have to very carefully apply some L'Hopital's rule to this, and you will find, again, if you use the same criteria, that c is positive. You have to get this in the right form, by the way, before you do a L'Hopital's rule, but this is indeterminate, right? Because it becomes infinity times 0 if you just plug in. That's one of our indeterminate forms. And this one, it turns out, also approaches 0, but do it. Make sure you believe that. Okay, so that one becomes 0. And then what do we end up with? We get 0 plus 0 plus 0 plus 1 over c, right? So our mean, our mu, for this distribution is 1 over x. It's 1 over c. So it's 1 over c. So you go back up, this 1 over c, if c is very large, actually 1 over c, the mean is very close to what would be the y-axis in general, right? And the tail, as this gets larger, the tail gets pinched down much more quickly, right? It gets pinched down much more quickly to keep that area equal to 1 underneath there. So that's the idea. So our mean, our mu, is equal to 1 over c for this distribution. All right, another recommended exercise, compute the median. So compute from this the m, the median for this distribution. For that, you just integrate the thing we've already integrated, and you find where is the area equal to 1/2, right? Where's the area equal to 1/2? All right, one final item that I would like to say something about. We're not going to do anything with this one other than I'm just going to draw you a picture and write the definition down. But this is an important distribution. It's called the normal distribution. We've talked about this a lot, and when you see the function, you're going to say that it looks familiar. So this is called a normal distribution, sometimes called a Gauss distribution or Gaussian. So Gaussian distribution, sometimes in some books. All right, so here's what it is. Remember, we have to define a probability density function for this to work out, right? So here's the formula. F of x is equal to, there's going to be a whole bunch of symbols in here that I will define in a moment. Really, there's only two, but that we don't know what they mean. But this is going to be 1 over sigma, that's got to be defined, times the square root of 2 pi. That's just a number, right? We know what that is. Times e to the power, and now the power is going to be minus x minus mu. This mu is just a symbol right now, but it's going to turn out that that becomes the mean. This is all over 2 sigma squared. So here, mu and sigma are constants. Sigma itself must be non-negative. It's got to be positive. Okay? So that's the criteria on the sigma. And how do these work? So by the way, mu we know. Mu, it turns out, I'm using the same symbol, not by coincidence, okay? Mu turns out to be the mean. So this can be computed. In theory. I'm going to put this in quotes. Actually, this one can be computed. The mean can be computed by you. You can compute the mean. There are other things that are not so easy to compute for this one, all right? But you can compute the mean for this one, can be computed. It turns out to be exactly mu. So if you work this out, you get exactly mu. Sigma is called the standard deviation of the distribution. So it's exactly what it sounds like. It tells you how much a standard change, a typical change in probability, how spread out it is. How spread out are the changes in this distribution. And the graph of this distribution, this probability distribution, looks like the following. I'm going to try to sketch it. It won't be perfect. All right, but it's going to look something like this, like a bell. You've probably seen these. That's a horrible picture. So it's supposed to be very symmetric, okay? So there's a bell. Now, in this bell, the midlight's supposed to be symmetric, so therefore the median is going to be equal to the mean. All right, but if you draw this vertical line that cuts right through the middle, supposed to, this is mu. All right, so that x value is mu. It shifts the kind of the bell shape. It shifts the bell, the hump of the bell. It shifts it around. And what does the sigma control? Well, the sigma is going to control how steep this is. So you could have a bell. Remember, the area under the curve has to be 1, right? So pretend that's symmetric. But the sigma is going to measure this. The sigma is in charge of this. So the standard deviation measures. You could also say the standard deviation measures the width in this direction. Okay, the difference from the mean in this direction. But it's just as safe to say that it measures this. Now, why am I just stating this? Why aren't we working this out? Well, look at the integrand here. This thing is like, so our f of x is similar to, it's got a bunch of constants here, right? Pi is just a constant, but it's similar to one of our favorite functions, right? E to the minus u squared. And as we know, this function does not have a nice simple antiderivative, a simple function antiderivative, and so this must be computed numerically. So we compute these numerically, or in Calc 3 you'll learn how to compute this. At least the integral of the integral to show that this one is equal to 1, you'll be able to show that in Calc 3 by other methods. So in Calc 3, not too far down the road, we'll learn how to compute that. So what do you learn in Calc 3? Mostly you learn how to compute this integral. So the integral from minus infinity to infinity of 1 over sigma square root 2 pi e to the minus x minus mu quantity squared over 2 sigma squared dx. This is equal to 1. That you'll do in Calc 3. All right, well, this is just an example of a probability density function. I'm going to leave this video here. You'll see examples of computing stuff with this given this fact, right? So in other words, you'll have to like find the mean, find the sigma, write down the formula, that kind of stuff in your homework. So you will see this distribution again, and you'll definitely have to compute means and medians and probabilities in your homework. So I'll leave this here, and I'll see you guys in the next lecture.